In this question, we are required to find the Taylor series expansion for f of x equals to ln x around x equals to 1. Now, we have already done this. I've already worked out this in a previous example, if you look at my previous videos. So what I'm going to do is just to copy it down. So from previous example, f of x is equal to x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to power 4 over 4, and so on and so forth. So basically what you have to do to get this, just a reminder, is you have to find the derivatives of this function at x is equals to 1. So, and that will give you the coefficients, and use those coefficients. You plug those coefficients into this formula for Taylor series. All right, this formula here, to be able to get what you need. Remember, this is centered at x is equals to 1, so a will be equal to 1. All right, so once you have that, we can carry on to b. Now, part b is using the 4th degree Taylor polynomial as an approximation for this function. Find the maximum error for values of x that are between -1/2 and 3/2, including both. All right, so we need to write our error term, and the magnitude of error is given by this formula, the nth plus 1 derivative at z multiplied by x minus so this is just a general formula of n plus 1 factorial. All right, now remember, this formula is the same formula as this guy here. All right, I'm using z instead of c, and c in place of x, but it's the same thing. It's exactly the same thing. But I'm just using this because I've used this in my previous videos. For consistency, I'll stick with that. Now, in this question, c is equals to 1. X is between 1/2 and 3/2, not -1/2. Including both, and n is equals to 4. All right, so we'll use this values to simplify this formula. So which means r for x will be equal to f 4 plus 1, that will be 5, 5th derivative of f at z. X is all right, x is between, now remember, c is 1. Whether x is 1/2 or 3/2, we'll still end up with the same magnitude of error. Magnitude of error. So for x, whether you use x is equals to 1/2 or x is equals to 3/2, you will still get the same magnitude of error. You will still get the same magnitude of error. Okay. So you'll still get the same magnitude of error, which means what I'm going to do, all right, what I'm going to do here is in place of x, I'll write 3 over 2. Remember, a half minus 1 is negative a half. Magnitude of that, absolute value of that is just a half. 3 over 2 minus 1 is a half. So we'll stick with 3 over 2. Okay, so 3 over 2 minus 1 to power 5 over 5 factorial give us now, all right, here, before I write this guy here, we can again get this from previous examples. Okay, so from previous example, okay, when we're working through a similar question, the fifth derivative of this function was 24 over x to the power 5. All right, so which means the fifth derivative of this function at z will be equal to 24 of z to the power 5 over z to the power 5. Okay, so which means my formula will be simplified this way. I'll have hence r for 3 over 2 will be equal to 24, absolute value of 24 over z to the power 5. Let me just put that in bracket. Multiplied by a half to the power 5 over 5 factorial. All right. Again, by inspection, remember we are dividing 24 by z to the power 5. Now, we are trying to find the magnitude of error. Now, if we plug in 3 over 2 in place of z, we won't get the maximum error as compared to when we plug in a half. If we plug in a half in place of z, then the error will be maximum. So by inspection, z there will be maximum error if z is equal to a half. All right, so when z is equals to a half, because you're dividing by a decimal, right? So if you divide by a smaller decimal, then you'll end up with a bigger magnitude. All right. So what I'm going to do is replace that in the formula. So r for 3 over 2 will be equal to the magnitude of 24 divided by a half to the power 5 multiplied by a half to the power 5 over 5 factorial, and that will give us a fifth. Okay,